Hi, I thought I'd do a little video about oscillators and dip meters. I haven't seen anyone do a video on dip meters, so I thought maybe I would do one. There might be some out there, but I'm not aware of them. So, first of all, this is a modern dip meter here. It's mostly used in RF circuits, 1.5 to 250 megahertz. This one works at. It comes in a little box like this, and it has um, a little crystal earphone which you can actually plug in the bottom over here. So if you are servicing a radio frequency circuit, you can actually listen to, if there's any demodulation going on, you'll be able to listen to it on the little earphone. And it comes with a bunch of little coils that work at different frequencies. The highest frequency one is actually a little PC board just with a trace on it like that. So inside of the dip meter, of course, there is an oscillator, and it also has a modulation tone, probably 1 kilohertz or something, that you can actually put in there. So as I said, it's mostly used traditionally by amateur radio people that have radio frequency circuits, but nevertheless, it's an interesting device. So what I have here is a simple one transistor and two resistors and three capacitor and a little coil, uh, Colpitts type oscillator. And so you can see over here there is a little coil here. There's a little ferrite slug in there to give it a little bit more inductance. That's why it's 7.2 microhenries. Didn't have the little slug in there, it would be more like 0.5. And uses a traditional standard, 2N3904 that are common here in the United States. Running it at 9 volts, and output is expected to be around about 8.5 megahertz. And indeed, I've got it running over here on this little toy oscilloscope. And if we look at the signal here, 8.4, 8.44, 8.47 megahertz. So let me put the camera back. So I'm going to turn it off. Wait for the signal to die down. Okay. So the way you use these things is you plug in the coil that with the frequency range you're interested in. This coil is on the yellow scale on there. You can see this faint yellow there, and it's 7 to 18 megahertz. Now, if I put this, let me move this over so that you can see what's going on. We need to be able to see this little scale. I'll see if I'll prop it up a little bit here. Yeah, it's a little bit better. So to check the resonance of like an LC circuit, you would turn on the power here. So it's starting to oscillate internally, and the oscillations, of course, are related to that coil. So that coil is radiating electromagnetic energy, and it is coupling into this inductor. So now if you twirl this I don't know if you can see it, but it's dipping down. So when it has the most dip in it is where the resonant frequency is, and as you can see, it is right between 8 and 9 megahertz here. 8 megahertz, and that's 9 megahertz. It's kind of smack bang in the middle, just about. Well, there's a little bit of parallax error with the camera. If I look at it with my eye, it is actually teeny bit more towards the 8 than the 9, which I guess was correct because it was oscillating at 8.4, 8.47. another way that you can use these is you can turn the power off, so now it's not oscillating, and you can put the coil right next to the inductor there and watch the meter there when I turn the oscillator on, and now it is picking up energy through electromagnetic coupling from the inductor to the coils and the opposite. And again, you can actually twirl but now it's the opposite. You're looking for the highest signal. You see the little, again, let me prop it up. See, the highest signal that we want. And again, it's the same thing. It is right between, about the same place, between 8 and 9 megahertz. So that is how this dip meter can be used. So you can imagine if you have especially old-fashioned radio frequency circuits that had all discrete components in them, coils, RF amplifiers, IF amplifiers. You could actually use a device like this to trace the signal through the radio from the antenna to the IF circuits and so on, and it would come in handy. And if you're creating a circuit, maybe something like this, only more sophisticated for your amplifier, you could actually test the resonant frequency and make adjustments. Adjust a little adjustable capacitor or trimmer capacitor or something like that. Like this particular circuit here, if you put a trimmer capacitor, maybe 10 picofarads or something, around this coil, you can actually fine-tune the frequency probably from 7 to 9 megahertz or something like that. So you might ask yourself, why would I want to use one of these things? Well, if you look at this circuit here, the formulas that they provide in textbooks and so on is the resonant frequency, and for a Colpitts type oscillator you have to take these two capacitors and find the total capacitance, which is less than the sum of them. So you have to calculate it by taking the product and dividing by the sum, and if you do that you end up at 27 picofarads. If you then take the 27 picofarads and the 7.2 microhenries and apply the resonant frequency formula to it, you'll end up at 11.4 megahertz. Or you can actually take a shortcut and use 0.159 divided by the square root of LC, which is not quite as accurate, but is a quick way. So anyway, this circuit here, as you can imagine, it has a 0.1 farad capacitor here. It is connected to the transistor, which also has some input capacitance and what have you. The two capacitors are connected to the emitter, and so there is some loading there, and it is actually how it provides the feedback. And if you connect something on the output there, it could actually load down the circuit even further and slightly change the frequency, but that's a different matter here. But if you want to find out what the thing is going to oscillate at, as you can see, when I took the dip meter, it was able to determine accurately that we are talking about 8.5 megahertz. But if you calculate it, you wouldn't know that. So this is an example where you can actually test a circuit to see, how it is responding when you can't accurately calculate something. So I thought that was an interesting example of how you can use one of these things. Anyway, I thought this might be interesting, so I'll put a little video up for it, and we'll leave it at that, and next time we'll try something else.